Welcome to the lair of the Batty Boffin.
Hi there Batty fans, time for a little more electricity with the Batty Boffin. Now in earlier videos we've talked about circuits where all the components are arranged all the way one after another around the circuit, arranged in series, with of course the exception of voltmeters which are always wired in parallel. But on this one we've actually got the components wired in parallel. My two resistors, R1 and R2, are like on the rungs of a ladder. They don't follow round one after another. So the electricity that comes around has a choice of either going through R1 or through R2. Whereas if they were wired in series, it would go through R1 and then R2. So this one's a little trickier to do because you can't just say the total resistance is R1 plus R2. It doesn't work like that. What we're going to do is take each little branch individually and we're going to apply Ohm's law, which I hope you remember that one. That's our formula triangle. Here's Ohm's law, V equals I times R, and we're going to apply that to each little branch. So, on this one here, rather than the current staying the same and the voltage being shared out like we did when we had the series ones, if you're not sure about that, go back and pop a look at the ones on series, things wired in series. Here, instead of the amps being the same all the way round and the volts being shared out, here the volts are the same all the way round and the amps are shared out. So, voltmeter number 1 is going to read 6 volts and voltmeter number 2 is going to read 6 volts because our battery is putting out 6 volts and everybody's getting 6 volts. So that means on this little one up here, we know R1, resistance 1 is 20 ohms and it's getting 6 volts. What's the reading on the ammeter? So you can pause the video, use Ohm's law and work that out now please. Right, we should get something like this. We want to know the reading on the ammeter. I is V over R. So in our particular case, the volts are 6 and the resistance is 20. 6 divided by 20 is 0.3 amps. So that ammeter is reading 0.3 amps. What about A2? Well, actually the figures are exactly the same. So that one will also read 0.3. So that's ammeter number 1. Ammeter number 2 will also be 0.3 amps. This means that we can now calculate the total current because the current adds up all the way round. The voltage is the same and the currents add up. When it's in series, the current stays the same and the voltages add up. So we can now calculate the total current around the whole series. This means that ammeter total, that one there, must read 0.6 amps. Because it reads 0.6 amps when it comes down here, 0.3 goes down that branch and 0.3 goes down that branch. And when it comes round back up here, if you had an ammeter here, that would read 0.6 again. So that gives us the total amps for the whole circuit. So using that, we can now work out the overall resistance because we know the overall amps, we know the overall volts, so that means we can work out the overall resistance. Back to our formula triangle again. Pause the video and have a go at that please. Right, let's do this one. Resistance is V over I. So this is resistance total equals V over I, which in the volts is 6, and our reading, our total current is 0.6 on there. 6 divided by 0.6. That's 10. If you're not happy with doing divides like this, check out some of the Batty Boffin maths videos. So that means that the overall resistance is 10 ohms. Now hang on, you might say, but that was 20 and that was 20. How come the total's 10? Well, it works like that. because the current has a choice of either going down that way or going down that way, it's kind of like an easier path. And when you wire things up in parallel like this, you find the resistance actually goes down. You actually, if you want to know it, you add the reciprocals, but that's possibly a bit further on than this here, but it's 1 over 20 plus 1 over 20 is 1 over RT, if you want to do that. So we've got an overall resistance of 10 ohms. The easiest way to do it is to calculate the current for each little bit and then top them up to get the total overall current, and then, like we did, pop it back into Ohm's law and you get the total overall resistance. Right, come back in a minute and there'll be one for you to have a go at. Right, here's one for you to have a go at. So here we've got a circuit very like the one we had before, with our two resistors, R1 and R2, arranged in parallel. This time though, they've got different resistances. R1 is a 10 ohm resistor and R2 is a 20 ohm resistor. So when we find that this current gets shared between them, they're going to have different shares. It's not like the last one where they took the same shares. So we're going to attack this the same way that we did before, using Ohm's law. V equals I times R, and there it is in your formula triangle. So what you need to do is, for each branch, you need to work out what the voltage is for each part. Of course, remembering the voltage is the same all the way through on things wired in parallel like this. So 6 volts, 6 volts, 6 volts. So you've got the resistance, you've got the voltage, you can work out the current using Ohm's law. You can do it for the first branch and then do exactly the same for the second branch. So when you know the reading on ammeter 1 and ammeter 2, you can combine those to work out the total amperage up there. So whatever this is and whatever this is, we add them together to get the total. Think of a river where two rivers flow together. Okay, you get the total up there. Once you know the total current for the circuit, the reading on that ammeter up there, we can put that together with our 6 volts to work out the overall resistance of these resistors combined. Please remember, in series we just added up the resistances. When it's wired in parallel, you can't just add up the resistances. So there's quite a lot to do there, but pause the video and have a go with that, and then we'll work through it together afterwards. Right, how did you get on with that? Let's work through it together. First bit, we'll do this one up here. We've got V1 is 6 volts. It's the same on this. When it's in parallel, all the voltages are the same. Resistance 1 is 10 ohms. And in order to work out I, the current, we cover up I and what's left is the formula. So V over R. So in this case, I1 is V, which is 6, over R, which is 10, which gives us 0.6 amps. Okay with that one? Now for number 2. Same thing again. V2 is 6 again. R2 is 20 this time, which gives us I2 being 6 divided by 20, which is 0.3 amps. And that makes sense because it's twice as much resistance, so half as much current going through it. That kind of makes sense, doesn't it? So what we're saying is that this 10 ohm resistor has 0.6 amps going through it, and this has 0.3 amps going through it. That means that the total overall amperage, the total overall current, I total, must be 0.9 amps. Did you get that? Good. Then we're going to do the stuff for the total. I'm going to change to red for the total overall things. So here I'm looking at the circuit as a whole. I'm going to use the voltage, which is the same, the total current, and then I'm going to see what the resistance of this is if you kind of smushed it all together. And it's not 10 plus 20, so the answer is not 30. So for the overall things, we have the total voltage is again 6. The total current we've just seen is 0.9. And to calculate resistance, we do V over I. So the resistance, total resistance, is V, which is 6, divided by I, which is 0.9. Please note that's 6 divided by 0.9, not 6 times 0.9. Okay, if you're not happy with dividing by decimals, check out some of the Batty Boffin maths videos, which will give you a hand on that there. 6 divided by 0.9 is 6 over 9 is 0.6 recurring, so it is 6.6 recurring. 6.6666666, 2/3, like. So we're out at 6.6 recurring, and the units for that are ohms. So this combined stuff here is equivalent to having one big 6.6 ohm resistor in there. You might be thinking, hang on, 10 plus 20 gives you 6 and a bit. That's weird, isn't it? But no, if you think about it, if this bottom bit were not here, then all the electricity would have to go through here and the resistance would be 10. But some of the electricity gets the chance of going down this one, so it kind of can bypass it. So the overall resistance is less than the smallest, and it always will be that. When you've got things wired in parallel, the combined resistance is always less than the lowest resistance. It combines like that. So there we go, 6.6 recurring is the answer for that. I hope you got that all right, and I'll see you next time, Batty fans.